Thank you. Hello, everybody. So I'm Michael. And well, I'm an atmospheric scientist. I'm mainly interested in processes, not so much in the grand scheme of things and the large picture. So this is going to be probably the least technical talk of all, though I haven't been to all the others. But I'm not only not a UKCA developer, but not even a UKCA user. So sorry about that, and apologies for that. But so we're going to talk about things with focus on how not only aerosols affect clouds, but what does that do to climate, and do things make sense in the way that we do consider them in models. So the focus of this presentation will not just be on this, the interaction between clouds and aerosols, but how do they affect climate, because it's pretty much one of the problems when people started to put in cloud aerosol interactions into global models like UKCA. They produced effects that they were just way too big to be consistent with observations from the last couple of decades. Just a bit of a recap and climate effects of aerosols, and I'll talk a little bit not just about the interaction between aerosols and clouds, but also how aerosols can affect clouds without influencing the cloud microphysics, which is typically what people think of if they think of aerosol indirect effects and how aerosols interact with clouds. But it's more than that, more than just cloud microphysics. So we do have the direct effect. There was a lot of talk already about that. So aerosols scatter and absorb radiation, and I'm just going to highlight one complication that the absorption has over the scattering. And then we have these indirect effects. And well, typically people distinguish between a first and a second, but kind of second is kind of a lot more than just one simple one. The first is relatively simple. So if you have more aerosol particles, then you tend to get more cloud droplets and also more ice particles. And then that leads to clouds that are more reflective, and you get a cooling in your climate that you simulate or that you produce. And then there are second indirect effects that essentially traditionally it's thought, well, that if I have more and smaller cloud droplets, then the precipitation efficiency is reduced, and that leads to more clouds that then again can reflect sunlight, and that leads to cooling. However, as I will point out, it's not cloud lifetime is not only influenced by the precipitation efficiency, but also by the way how dry air or environmental air mixes into clouds. And that can, in the end, essentially dominate cloud lifetime effects over these microphysical effects where the formation of precipitation is altered. And then there are other effects, in particular semi-direct effects, and they can have cooling or warming effects on climate. Overall, aerosols are thought to cool the climate, and that's the last figure from the last IPCC report, the fifth one, where you have forcing for long-lived greenhouse gases on the top, and down here is one of the main cooling agents due to anthropogenic activity. Here are the aerosols, and you see black carbon is absorbing, is warming, sulfate and others are cooling. And then here is kind of a number for the main topic of this presentation, the effect of aerosols on clouds. And this is really just only cloud brightening, which leads to more reflective clouds and to a cooling. But what you can see overall is, so the anthropogenic greenhouse forcings, if you add up these numbers here, is about 3.3 watts per square meter for the year 2011 or 2010, I believe it is. And the aerosols lead to a cooling, so that overall the anthropogenic forcing is 2.3 watts. However, there's a bit of an issue here. And that is, if you add up all the numbers that people have produced to quantify aerosol effects, then you can come up with numbers that are larger than the forcing due to greenhouse gases combined. And that's how it sort of goes. So you have the aerosol direct effect, and that's kind of the range given in the current IPCC report. The upper limit has been reduced down a little bit from the last report, but you can get up to minus 0.77 watts per square meter. The first aerosol indirect effect, a wide range up to exceeding up to minus 1 watts per square meter. And then not included in the IPCC report, since it's treated as a feedback and not as a direct forcing, is the second aerosol indirect effect, and the estimates go up to minus 1 watts per square meter or even larger. So if you just add up all the large end, then you can get numbers that can't be true, because we did have a warming, so it wasn't a cooling that we had over the last century. So there is a bit of a problem, and this is kind of the main theme of my presentation today. So what is going on here? Because it's thought that this minus 0.77 watts per square meter is pretty much as likely as all the other numbers within that range. So something is going on here. And let's just go through these individual effects, direct, semi-direct, and the various indirect effects one by one. So just briefly, the direct effect is believed to be fairly well understood, as we have more and more observations also from satellite, and the models become more sophisticated, just if you think back of what we have heard about the UKCA. So we now have modal representation, so we not only have aerosol mass but also number, and we have complex interactions not only within the aerosol phase but also with the chemistry, with the clouds, so tons of things going on. So there is still a number of active research areas, and I'm going to highlight some of those next. But first, before we start, why is radiative forcing such a powerful, believed to be such a powerful concept? And that is, people are estimating radiative forcing to be able to tell something about the change of near-surface temperatures. The conventional wisdom is that there is a one-to-one correlation between forcing and global mean surface temperature, independent of what is causing this forcing. And as I will show, this is true for some forcings, but not for all. In particular, it's not true for all aerosol forcings. But to make my point, let's start off where it works. If we have non-absorbing aerosols and only consider direct effects, then the non-absorbing aerosols like sulfate aerosol, sea salt, will reflect solar radiation, and pretty much there will be no absorption whatsoever. So then there is less radiation that's absorbed in the system, so that leads to a cooling of the atmosphere. It's slightly modulated by the surface albedo, so if you have a high reflective surface like desert or ice, then by adding more reflectors you're not going to change much, because instead of being reflected at the surface, radiation gets reflected at aerosol particles. So it's not the same forcing everywhere, it depends at least on the underlying surface. But what you have is essentially the amount of radiation that is reflected out back to space is exactly pretty much the reduction of radiation at the surface. So if you measure forcings at the top of the atmosphere, then you also have a direct measure of what's going on at the surface. So you can estimate the surface temperature change from the top of atmosphere radiative forcing. So there it works. Now if we come to absorbing aerosols, then essentially they at least partially absorb solar radiation, so this can't be reflected elsewhere, so less radiation is reflected back to space, so you keep more energy in the system, so you warm the atmosphere. However, if you have an aerosol layer, absorbing aerosol layer aloft, then the absorbed radiation does not reach the surface. So this can lead to a surface cooling, although you warm the atmosphere overall. So this means, and there's another point, that the reduction in downward radiation near the surface can be much larger than the reduction of outgoing radiation at the top of atmosphere. So here, this concept where we try to measure a change in surface temperature by forcing does not work, because for once it does have the wrong sign. So although it's a warming of the system overall, it's a cooling at the surface. And also there isn't a one-to-one relationship, because there's always going to be some reflection going on. So only for a particular type of aerosol in a particular location within the atmosphere, you would be able to construct such a relationship, but it just wouldn't be universal. Just to back this up with numbers, so this is from the INDEX experiment, one of the very big experiments in the, I guess, in the late 90s. Yeah, these are data from March 99, quite a while back, but it's very difficult to run these big experiments on a regular basis. So I think there has been nothing on that scale since. So these were experiments done over the Indian Ocean, and Ramanathan just coined the wording or the expression of the brown cloud, the Asian brown cloud. So there was a lot of absorbing aerosol in the boundary layer over the Indian Ocean, just coming from a continental outflow from India. And so they were measuring then radiation at the surface on ships. They did in situ observations with airplanes and remote sensing observations with airplanes, and then they had satellites, and then they combined all together and just came up for this particular month, or this series of months from January to March, with forcing estimates for the direct aerosol effect. And as you can see, it's a cooling overall. So we cool the system in this region by -7 watts per square meter. But due to the absorption going on, so there's 16 watts per square meter that gets stuck in the atmosphere, there's a much stronger reduction at the surface of -23 watts per square meter. If you then add clouds to it, the difference between top of atmosphere and surface remains pretty much the same. So it's something like close to, what is this? This is 18 watts per square meter. This is 16 watts per square meter. The absorption goes up a little bit because you have multiple reflection and enhanced absorption. But now what you see is at the top of the atmosphere, forcing is almost consistent with zero, whereas we still have a strong forcing at the surface. So that's not particularly good if you think in IPCC terms and radiative forcing. With indirect effect, at least for the first indirect effect, things work because that is purely reflective. So the change in radiation that you see at the top of atmosphere due to this effect is the same that you get at the surface. So for the first indirect effect, things work, but for the seconds they don't, as I will show later on. Okay, but so this is even more of a problem, because I've shown you before that kind of adding up the top of atmosphere radiative forcings for aerosols can lead to more aerosol cooling than we have had greenhouse warming, and we are living in a warming climate, as we know from temperature measurements. So if you just take a surface perspective here in terms of radiative forcing, then you even have more cooling, so you have even a bigger problem here with aerosol effect. So people have thrown in all these effects into the models, and they just kind of got way too much cooling initially. So the first studies came out. They just, for example, Abdul Herzog and Steve Garn, the work they did, this is kind of the scheme in the UKCA. I remember getting their publication to include in the third IPCC assessment report. They came up with cooling figures in the order of 5 watts per square meter for the first and the second aerosol indirect effects. So they're smaller now, but there is still this problem that they tend to be too large. So one of the things that can save you are other effects. that might or might not be included in your models, at least not as good, maybe. So semi-direct aerosol effects is if you have an absorbing aerosol layer away from the surface, then it will warm this layer, and that will lead to a more stable atmosphere. So you have less warming at the surface, more warming higher aloft. So that reduces vertical mixing, that reduces low-level cloud, and that leads to a surface warming because you have more clear sky, more radiation can reach the surface. And as it turns out, the semi-direct effect can be several times larger than the direct effect. So there is a warming effect. And if you're interested in the net effect of aerosols on climate, then this is really something you shouldn't forget. Typically, that's represented in models because aerosol particles are radiatively active, so that then affects the vertical structure of the atmosphere, and then the cloud scheme and the convection schemes and the explicitly resolved circulation will do something with that forcing. Okay, so then there is another thing that is different to forcing, aerosol forcing, compared to forcing from well-mixed greenhouse gases. Aerosols are highly variable in space and time, although Paul said long lifetime of days up to weeks, while they're still confined to source regions. So which means that in contrast to well-mixed greenhouse gases, aerosol forcing comes in patterns that induces additional gradients, that produces additional circulation changes, and that can lead to some unexpected effects that can have regionally at least warming or cooling effects. And they can also affect the hydrological cycle. Two quick examples to that. One is the winter warming followed after volcanic eruptions. What these volcanic eruptions do, at least the big one, the stratospheric one, like Pinatubo in 1991, they put a lot of SO2 into the stratosphere where it oxidizes to sulfate to produce sulfate aerosol. That can stick around in the stratosphere for pretty long times, for order 1 to 2 years. So you get a much larger effect there because of the prolonged lifetime compared to tropospheric lifetimes. This aerosol not only reflects solar radiation, but there is some absorption going on due to the size of these particles in the near infrared. So part of the solar radiation gets absorbed, so this aerosol layer gets warmed. You have more solar input in the tropics than in the extratropics, so that creates a large-scale gradient, which the troposphere warming, more warming in the tropics than in the extratropics, and that differential heating leads to a strengthening of the polar vortex during wintertime. This has an effect on the troposphere, and on the northern hemisphere everything maps onto the North Atlantic oscillation, and so this feedback leads to a strengthening of the pressure difference between the Icelandic low and the Azore high. You get a more zonal flow, which then leads to anomalous warm temperatures over Eurasia and North America. So although we have a clearly cooling aerosol, sulfate aerosol, the cooling dominates, there is still regionally, there are areas where you can have a warming. Overall, if you do the global average, it's going to be cooling. But so there is this circulation change that can introduce regionally a warming. Another one quite interesting, and it affects clouds and the hydrological cycle, so that's why I bring it up here, is the potential drying of the Sahel zone due to anthropogenic sulfate aerosol. So as Paul has already shown this morning, a lot of anthropogenic aerosol source regions are confined to the northern hemisphere. In this model study here by Leo Rothstein and Ulrike Lohmann, they focused on sulfate, and so most of that, the anthropogenic part, is in the northern hemisphere. That creates a hemispherical gradient in sea surface temperature, and that causes a southward shift of tropical precipitation. if you, in this model, the Australian model, if you include aerosol indirect effects. And I'm going to show you next what effects these are. So that's, again, aerosol forcing comes in pattern, even if this is now a hemispherical, so a pretty large scale pattern. So this can lead to a shift in precipitation zones. And there is some evidence from observations. What this shows is going from the deep south minus 80 degrees in latitude to plus 80 in latitude. So from the south to the North Pole, and then averaged precipitation over, so shown as an anomaly between the last 100 years and present day. So present day in this case, the year 2000. And what you can see is that there was more precipitation south of the equator and less north of the equator. And this model can only explain it or is able to explain it if you include aerosol forcing and aerosol indirect effect, so the effect of aerosols on clouds and the hydrological cycle. So which is quite interesting because that seems that essentially the industrialized nations are responsible for famine in the Sahel zone. So there was a bit then, people were just claiming, well, this is evidence that the industrial nations should pay countries in the Sahel zone for the problems they have with drought. Okay, just that's not what I want to focus on for the rest of this presentation, but talk more about the aerosol indirect effects and why, again, we might have too much more cooling than there actually is, and that there's something missing in the models. Okay, so first, quick look on clouds. How do clouds affect the radiation balance? So clouds do reflect solar radiation, and actually they're the dominant factor in the planetary albedo. So they really dominate what's reflected in terms of solar radiation. So overall, 30% of the incoming solar radiation is reflected, and over 22% is done by clouds. Clouds are also active in the infrared, so they absorb outgoing long-wave radiation to a significant amount. And if you do the numbering, then cloud forcing turns out to be a strong cooling in the short wave and a warming in the long wave. And the net effect is on global and annual average something like minus 17 watts per square meter. However, cloud forcing, the net forcing, is the difference between two relatively large numbers. So if you only change the individual numbers by a small percentage, you change the net effect potentially by a much larger amount. So that's why a relatively small effect can have a big impact on the forcing of clouds. And then not to be forgotten is phase changes here. Aerosols can also affect the when, where, and how much phase changes happen. And that's an important heating component. The latent heat release is an important component in the energy budget. If you compare that to the solar incoming, then it's over 20% of that is due to latent heat release. So that's forcing of clouds. Let's look into cloud formation. So without aerosol particles in the atmosphere, we wouldn't have any clouds, any precipitation. So if clouds would need to form out of the blue, then you would need relative humidities that you would never observe in the atmosphere. So we would only have dew formation at the surface and nothing going on within the atmosphere. So we can be pretty happy that we do have aerosol particles in the atmosphere naturally, because we tend to kind of think about, when we talk about aerosols, just kind of what is the anthropogenic perturbation of that. But so there are these particles and they form cloud condensation nuclei. Many of them are of anthropogenic origin, and depending on their size and their chemical properties, they can be activated to form clouds or not. And so that's, I think, in the UKCA, Steve Gahn's work is used to parameterize these effects. But I'm not going to focus on the mechanics, on the aerosol activation and how the microphysical processes work in detail, but just again look on the effects and how that then impacts the radiation balance overall. So we do have the first aerosol indirect effects, as I've already said. So if I have more aerosol particles around, I have more CCN cloud condensation nuclei. Given that I have the same amount of water available for phase changes and to form clouds, this will lead to smaller and more cloud droplets and more reflective clouds. These smaller cloud droplets will grow much slower to form precipitation, so that means you would form more clouds that are more longer lived, and that, as I've said, can offset greenhouse gas forcing, at least qualitatively. So if we want to then, well, first, before we come to methods how to estimate this qualitatively, just observational evidence, and I think you've seen that in talks before, is shipwrecks are probably the best example, a manifestation of the first aerosol indirect effect. So you have these ships putting out quite a bit of pollutants and aerosol particles that if they enter a marine stratocumulus can influence cloud properties by forming brighter clouds, and you can see these cloud streaks here. So this is not from aircrafts but from ships that emitting pollutants into a cloudy, a layer that can potentially form clouds. So there is very strong evidence that this exists, but how do we get these numbers here? And that is, if we want to have global estimates, then we need to use global models. And then we're stuck with problems that these models have to represent clouds. And this is trying to give a true representation of clouds in a climate model. Say this is a relatively old figure from the climate prediction model. So this is the unified model in a pretty old version. So now we have kind of CMIP type simulations for the IPCC report are at least twice that resolution. But if you just focus on the British Isles with this resolution, you have about 2 to 6 grid points that represent all of the British Isles. If you double that resolution, so instead of 2 by 3, you have 4 by 6, so you have 12 grid points, so still not too impressive to really represent actual clouds if you look at satellite images. And the main issue here is that we want to use climate models for climate, right? So we need them to run for decades and centuries in a decent amount of time. So they have to be a lot faster than reality. And so that kind of restricts the spatial resolution that we can use. So now I think we're sort of down to 1 degree resolution with the increase in computer power. One of the problem and limits in increasing this spatial resolution further is the additional complexity that, for example, models like UKCA have. So if we want to simulate a full carbon cycle, then we need chemistry. If we want to have full aerosols effects, we need interactive aerosols. That makes these models a lot more expensive and limits the additional spatial resolution that we can afford. Also, we're then interested in pretty much aggregated quantities, and we're interested in climate and not just in weather. So we're more interested in what's going on a monthly or annual basis than what's happening on a daily basis. So that's kind of the justification for what we're doing or how we run our climate models, but it has major shortcomings. Clouds are unresolved because they're much smaller than if you have a 100 by 100 kilometer grid. That's 10,000 square kilometers. So you can imagine that clouds typically are smaller. So, and then vertical motion, convection that produces clouds is not resolved and needs to be parameterized. And on top of that, your aerosols do something. So clouds and precipitation are relatively poorly represented, and they're actually the biggest uncertainty in climate sensitivity. So how much warmer does it get if we double CO2 in the atmosphere, because the clouds respond to the changes in the climate that's introduced by the change in greenhouse gases. And on top, we're just kind of perturbing something that we don't represent pretty well. So then what I was thinking is, well, if we have all these problems in the global model, if we really want to understand quantitatively what is going on, then we should use high-resolution models, and we should try to back up that with observations. And that's kind of what I've done a number of years back. Really would like to do more work on that. But let me report on what I've done pretty much 10 years ago now. So work was based on a field experiment, the ACE2 experiment, which was an aerosol characterization experiment close to the Canary Islands. So what they did is they went out to the Canary Islands, flew over the Atlantic, and sampled clouds and aerosols within a maritime stratocumulus cloud layer in the subtropical regions, Canary Islands. And luckily, they were able to observe 20 years ago, it is now already, for the observations. The model study is 10 years old, so it goes all pretty much quite far back, but still kind of state of the art, I would claim, if you look at the results at least. So in June, July 1997, they were able to sample air masses that were very different in their aerosol characteristics. So they had air masses coming from the west, so from the open Atlantic. So these were marine aerosols that were relatively clean, low aerosol number concentrations, and they had days where they had the air masses coming from the African continent that were highly polluted. So then they did measurements in those air masses, looked at the cloud properties, and found smaller cloud droplets in the polluted case and said, hooray, we found a first aerosol indirect effect. That's the number, that's the forcing, right? Problem with that study is that observational study is that not only the aerosol regime has changed, but also the meteorology. So the atmospheric conditions are very different. The stratification, the amount of moisture available, temperature, right? And in the observations, you cannot distinguish between the two. But in a model, you can, and then you can look at things in much more detail. And then on top of that, in a model world, you're able to then not only look at a first aerosol indirect effect, but also at cloud lifetime effect. And that's what I did, and that's what I'm going to report on next. So the model that I used is a high-resolution model that I've developed myself over a number of years. And I think the main point to take out from this slide is this resolution here. So climate models are in the order horizontally of 100 kilometer. I use a model 100 meter, so we can explicitly resolve most of the cloud formation processes. Vertically, it's 30 meters to resolve stratification and details more in the vertical than in the horizontal even. With this model, I can't afford to run globally, so it's a relatively small area, so sort of 20 by 20 kilometers is what we used. And so to give air masses enough time to develop, so when clouds left the model domain, they entered the model domain on the other side, so that we could just kind of observe and simulate them over longer periods of time that was longer than just the residence time of these clouds in our model domain. We started from 0 clouds because we didn't have observations really available, but we used forcing for temperature and humidity. So this represents large-scale advection of air masses into the model domain that happens in the real world and that we can't kind of explicitly simulate in this small model. So we had high resolution, did everything we could to reproduce what was observed, and then in the cloud microphysics, we added an interaction between aerosols and cloud droplets. So that was mainly due to an aerosol activation scheme where we predict cloud droplet number concentrations based on aerosol particles and number of CCN present, and then followed through then with all the processes in the microphysics. So if the cloud droplets were smaller, then it took them longer to produce precipitation. Also freezing processes were changed by that, although in this particular case, this is warm microphysics only. So makes the case a little bit simpler. But so what we had is aerosols, clouds, we had them interact, not just kind of based on the first aerosol indirect effect, but also cloud lifetime effects. And what I should have pointed out is that we had interactive radiation. Yes, so the dynamics is fully coupled to what the aerosols is doing, right? Cloud properties change, radiative properties change, and that then changes what the cloud dynamics and what the cloud formation processes are doing. So if you do these kind of studies, modeling studies, you best establish that your model is doing the right thing, so you should compare them with available observations. And so we took the data from this ACE2 campaign and compared them to what the model did for a particular case. This here is the clean case with the low aerosol number concentration in the atmosphere. And we looked at various quantities related to clouds. Let me just focus first on the cloud liquid water content. Here are the observations. So each dot is an observation through the cloud field, and they scatter uniformly here with height. And the amount in grams of water per cubic meter increases as you go up in the cloud. So this is cloud base at 1,200 meter above the surface, and cloud top is at 1.45 kilometers altitude approximately. This line here represents an adiabatic ascent of a parcel and the cloud liquid water that it would have. And so all the observations are to the left of that, and that represents or is indicative of mixing of dry air into your cloud as it develops and air rises within that cloud. So this mixing reduces the cloud liquid water content. If you compare that with the model, then strikingly you see that we only have numbers at discrete levels, and that just kind of represents the vertical resolution of our model. So we have data every 30 meter because that's the grid spacing in the vertical. And we get some spread because we sample at a constant altitude through the domain of the model, and wherever we have clouds, we get an entry here. And if you compare the two, they look very similar, and so we get this drying further up into the cloud, and we do get this right amount of water. So if we want to look then, there's our indirect effects. The main thing to get right is the size of your cloud droplets. And that comparison is shown here for the observations going from cloud base to cloud top. Size here of our cloud droplets from 0 to 35 micrometers. And as you can see, cloud droplet size increases as you go from cloud base to cloud top. Again, this line here would be for a cloud or for a parcel that ascends adiabatically with the cloud droplet number concentration that we observe at cloud base. So that's a very good predictor for the size of these cloud droplets, and we get a very good agreement between the model and the observation. So that kind of gives us confidence in the model setup that we're able to reproduce the atmospheric conditions and produce the clouds that was observed. And now we can do the games that you can't do with the observations. So we can keep the aerosol environment the same and change the meteorology. So we swap, so we have the clean case and the polluted case for the observations. So what we did and what I showed on the first slide was the clean aerosol with the meteorology for the clean case. And now what I'm showing here is a simulation with the clean aerosol in the polluted atmospheric state, so the polluted meteorology. So then I compare that with the case where I had the meteorology from the clean case. So here, what I've shown, so the previous slide had the cloud shown at a certain time at local noon of a particular day. That's where we have the observations. So that's what these black stars are about. And the vertical line is the uncertainty in the observations. And then for the model, we can show the same quantity as a function of time going through a day from 0 to 24 hours here. So this starts sometimes before sunrise and goes then through a 24-hour cycle. Shown here is, for example, the cloud fraction, and the solid line is what corresponds to the observed case, clean aerosol, clean metrology, so that's clean aerosol, CA, CM, clean metrology. And the dashed curve here is where we use the metrology for the polluted case. So now let's first look again. So we have essentially the same atmospheric conditions, but different aerosols. So we should see first aerosol indirect effects, which is we have gone to something. No, let me see. I was just saying it the other way around. What we kept constant the metrology. We want to see an aerosol effect. Bit of a rewind, but doesn't change the argument much. So we keep the clean metrology, but we change the aerosol because we want to see an aerosol effect, right? So the solid curve is what I've said before. So that's the clean aerosol, clean metrology. The dashed line is still the clean metrology, but with the polluted aerosol, right? So by increasing the aerosol number concentration, we should see an aerosol indirect effect. That's what we expect, and that's what we know from satellite observations already, and that's quantified here. So instead of having then in the mean at local noon something like cloud droplet size of or diameter of 15 micrometer, so this goes down to 10 micrometers, so we have a clear aerosol indirect effect. And then the next thing is we want to look if there is a second aerosol, a cloud lifetime effect. So what we would expect is that if there is a cloud lifetime effect as proposed by changes on the microphysics, so we just have smaller cloud droplets that grow slower, so we have less precipitations, we are left with more clouds, then we should see an increase in the condensed water phase. And what this shows is all the condensed water in the simulation throughout the domain as a function of time. And so if this simple cloud lifetime effect would be correct, then we would expect that the dashed curve is above the solid curve. And it isn't. So this is definitely counterintuitive and doesn't work with the simple second aerosol and indirect effect that a lot of people try to include in their global models. So there is a problem. And the issue is in both the cloud fraction and the amount of water that these clouds contain. So what we see is we see a decrease in the amount of clouds. So there are less areas that are covered with clouds. And where we have clouds, they contain less water. So then the big question is, why is that? And the main reason here is that in my model, the clouds do something that they typically don't do in a global model. Global model doesn't resolve individual clouds. They need to be parameterized. Here I can explicitly simulate their dynamics. So if I have brighter clouds, that changes the stratification of within the atmosphere, in particular at cloud top. That leads to more entrainment, mixing of dry air above the cloud into the cloud, and that dissolves the cloud. It's a cloud lifetime effect, aerosols affecting cloud lifetime, but it's not the effect that a lot of people just think of, where they just say, well, it's a microphysical effect. So this is a dynamical effect where clouds are dissolved by entrainment, and so cloud lifetime is changed by that effect and not by microphysical effects. And if you kind of look at clouds, then essentially precipitation is a pretty inefficient process to dissolve and remove clouds. It's mainly done through entrainment and evaporation of cloud droplets. So, and you don't typically include that in the typical parameterizations that are used in the model, because there you can't couple the cloud dynamics with the cloud formation in these parameterizations. So then if we just try to put some numbers onto it, so just to see how important is this effect so that we have more drying and less clouds. We calculated some numbers by just taking the clouds that we get with the clean metrology and the clean aerosol, and just pretend that what is just happening when we just make these cloud droplets smaller, as we would expect from this increase in aerosol number concentration. So this is really just taking the cloud field, the original cloud field, and just changing the radiative properties. And so, wait, this is the first aerosol indirect effect. So, sorry. So, wrong order a bit. So this is kind of, so this is, I thought this was the first number, but this is the second number. So the second number is just what I've just said. So we take one simulation for the clean case. We change the aerosol properties and the radiative properties. We repeat the radiative transfer calculation, and we get a cooling, a first indirect effect of minus 20 watts per square meter. So then, to estimate cloud lifetime effects, we compare the total aerosol forcing between the two simulations. So where in both cases we had the clean metrology, but different aerosols regimes. So, and we have, with the polluted case, we have fewer clouds. So this means we have less cooling than we have if there would only be a first aerosol indirect effect and no cloud lifetime effect. So this then means if you just take the difference, so then the lifetimes effects don't produce a cooling, but they produce a strong warming, which offsets 50% of the first aerosol indirect effect. And typically, if people include cloud lifetimes effects in their model, it always is a cooling, it has a negative sign. So it means there are really processes that are typically not included in global models. So there is some work that needs to be done. However, it's not so easy to do because this is something where the cloud microphysics interacts with the cloud dynamics, which typically is not resolved. And the big problem here is if you want to cast that into a modified parameterization is that this effect is strongly case dependent. So we, for example, did this. Here I focused on the clean metrology. We did the same study with the polluted, a different metrology. There we get less change of mixing of dry air above cloud into our cloud layer. So the cloud lifetime effect for the other metrology is close to zero. So that means it's not just a simple, I know my aerosols, I know the cloud lifetime effects, but you have to know a lot more, and typically you don't have that information available in a global climate model that is not able to resolve individual clouds. So to quickly summarize, so aerosols can partially offset greenhouse gas warming, and so this is also taken as a motivation to think about how we could intentionally change climate through geoengineering, but that wasn't the topic of this presentation. Aerosols are definitely necessary to form clouds, and if you change your aerosols, then you change your clouds, and those are the aerosol indirect effects. And so, however, it's quite difficult to quantify these effects. So the first aerosol indirect effects is relatively straightforward, but cloud lifetime effects are quite difficult to do because we need global models that don't have a good handle on these cloud dynamics and the cloud formation processes. So by design, these models cannot adequately capture all the relevant processes and feedbacks, so which means there's a lot of work needed, and I would argue with high-resolution models first to learn something about the processes so that we can improve then global climate models and models like UKCA so that they have a more complete representation of relevant processes. And I've only very briefly mentioned the ice phase, and if you go to the ice phase, so clouds are or liquid phase relatively simple because you just kind of, you have two categories like cloud droplets and precipitation droplets is a pretty good one. But if it comes to ice processes, things become really, really messy because shape and form become much more important, and even the simple microphysical processes without the aerosol interaction strongly depend on shape and history of these particles, and then it becomes really messy and complicated. So you can still build, I think, a career on trying to do better on ice phase processes. So as I've shown, we already have problems with the liquid phase. The ice phase is a different world and an even bigger challenge. And I stop here, and thank you.